Well, greetings everybody. I want to make this video to talk about two examples about power series. The first example you'll see right here. The other one that I'll get to later in the video is here. Okay, so if you're interested in either of those, this is the video for you. Now, in this first example, it says we're given a power series and it's asking for the radius and interval of convergence. Now, I will show you how to solve that, but I think it would be best for this video to explain a little bit about what a power series is and show you why this is in fact a power series. Okay, now that's not part of what this question asks, but it won't take me very long to do, and you should know what a power series is anyway. So I'll tell you. Now, here it is. Let's say that I'm given this series. I take that for granted. That's what I'm working with. Let's say make the first issue like this. What is a power series, and is this a power series in particular? Now, if I say go to a textbook or something like that and I look up the definition of a power series, what I'll see is that it's a series that looks like this: a constant plus another constant times x minus some number a to a power, plus another constant times x minus a to the next highest power. All these powers are positive whole numbers. So I get a constant times x minus some number to some whole number power. And then it goes on from there. Okay, now why is it written two different ways here? Well, these are the same thing. It's just that this first one is what this power series would be if that number a were 0. But that number a is some fixed number in every term. And so are these coefficients, C0, C1, C2, on and on. Okay. Now, if I write out some of the terms of this one, I'll see that it takes that form. So here, the series starts at 7. I'll put 7 for k and so on. I'll get the first term to be 7 to the 6th power times x minus 3 to the 7th power. I'll get the next term to be 7 to the 8th power over 8 times x minus 3 to the 8th power. Then 7 to the 9th power over 9 times x minus 3 to the 9th power. Now, every one of these terms takes the form that it says it will take over here. I'll get a constant, such as 7 to the 8th power over 8, times x minus some fixed number, which is 3 in this case. That number is called the center of the power series. And then to some exponent, which is a positive whole number. Okay, every term is going to be like that. That's what makes this a power series. We could say this is a power series centered at 3, in fact. Okay, so that's what it is. It's a power series. Now, let's talk about, with that out of the way, what the radius and interval of convergence is. Okay, so how we solve for that is we solve the ratio test for convergence. Here's what I mean. So let's see. Here's the ratio test. This is something that we've talked about before in the class. And it says if you have some series, and we'll call the formula for that series a subscript k, and you solve this limit k goes to infinity, a k plus 1 over a k, absolute value, and you get a number less than 1, that series converges. So what we'll say then is that if you want to know what it's going to take for this series to converge, which is what we're looking for at this point, that's what the interval of convergence is. So if you want to know what it's going to take for that series to converge, just set up the ratio test so that that happens. Set it up so that this limit is less than 1. Why less than 1? Because that's the case of the ratio test that would force the series to converge. So you just solve it that way, and whatever answer you get out of it is what's required for it to converge. Okay, so I will solve this statement for x. Okay, I will solve this combined limit and inequality for x. Now I'll do that in 3 steps because otherwise there's a lot happening here and I don't want all of it to blend together. So I'm going to do 3 separate things. I'm going to simplify this expression inside the absolute value. That'll require a little bit of algebra. Then I'm going to calculate the limit. Okay, and then my last step, I'll solve it for x. Okay, so first step, algebra. I'll simplify a k plus 1 over ak, with ak being the formula that was given in this series. Now, ak plus 1 over ak is this right here. Okay? All right. Oh, wait, this is a fraction. Why I didn't write this as like this divided by this other thing. The reason I skipped one step ahead, if you divide one fraction by another, which is what that's going to look like, that's the same as multiplying by the reciprocal, and I've started with this step here. Now, as far as how to simplify that, I would think that similar things would reduce with each other. So, in other words, I would think that the 7 to the powers k plus 1 and k, that they would probably cancel somehow. So I'm going to write them together just to make that look more easy and obvious. And then I would think the x minus 3's to the powers k plus 1 and k, that they would cancel with each other. And then maybe with the k terms, like k and k plus 1 itself, that maybe they would cancel with each other. Okay, so I do that and I see that they do cancel, like the 7's and the x minus 3's do cancel. Here's how. So we have something of this form. I've got some base number or base thing, b to the power n plus 1 over n. The way that those cancel is that I could factor this. I can factor b to the power n plus 1 as b to the power n times b to the power 1. Why can I do that? Well, because when you multiply like bases, laws of exponents say that we add the exponents. So if you can go one way, you can go the other way. Okay, so b to the n power times b to the first power is in fact b to the power n plus 1. So I could take that back apart. Why would I take it apart? Well, then these two terms cancel. Okay, and I'm left with just b. Now that is how 7 to the power k plus 1 over 7 to the power k cancels to just give you 7. X minus 3 to the k plus 1 over x minus 3 to the k cancels to just give you x minus 3. Now k over k plus 1, nothing can be canceled there. That part can't be reduced. We're just going to have to accept that it's there and leave it and worry about it later. Okay, so right there, that would conclude step 1 of just simplifying. Step 2, well, let's take care of the limit. All right, now that we've got it simplified. So what's the limit as k goes to infinity? K over k plus 1 times 7 times x minus 3. Now, if k goes to infinity, that's not going to affect this 7 right there. And it's not going to affect what x does either, because x is different than k. K going to infinity is only going to affect or determine what k over k plus 1 is. Now, if k goes to infinity, k over k plus 1 has a limit of 1. All right, so this expression that I ended up with in my first step, once the limit is applied, is going to be 1 times 7 times x minus 3, or just 7 times x minus 3. So here's what we've done so far. I simplified that interior expression. I've evaluated the limit. The last thing to do is just to solve what's left for x. Okay, so I get this absolute value inequality, which I will have to solve for x. Whatever I get as an answer out of that will be the interval of convergence. It'll be the values of x that will cause this series to converge. Okay, all right. So I solved the inequality like this. Absolute value inequalities expand this way. Okay, I'll divide both sides, or sorry, all three parts by 7, and I'll get that. And then I'll add 3 to all three parts, and I isolate the x in the middle, and it gives me a definitive statement about the x. It says the x needs to be between 20 over 7 and 22 over 7. Those values of x will cause this series to converge, and that's what the interval of convergence is. Now, it turns out that's just a preliminary answer. Yes, the series that we started with, it'll converge if x is between 20 over 7 and 22 over 7. But it turns out that it also may converge at the endpoints. It may converge individually at 20 over 7 and 22 over 7. Do you see why we have to check that? Do you see why that is? Well, we're setting up the ratio test so that the series we started with converges, and we're solving it backwards. Now, if that value right here, that limit, is less than 1, it'll converge. But what does it say if it's equal to 1? It says the test is inconclusive. What's that mean? Well, it means the series could converge or not, and the test doesn't say. Now, at the endpoints, 20 over 7 and 22 over 7, this limit would be 1. and the test would be inconclusive. So that's why we have to check the endpoints, because maybe they work, maybe they don't. Okay, so here's what we'll do. We will take those endpoints, 20 over 7 for x and 22 over 7 for x. We will put them in this series, and we will see in a case-by-case basis if it converges or not. Okay, so let's do that. First, I'll take this series. Do you see where the x is right there? Okay. I'll put 20 over 7 for the x. Here's what you'll get. 7 to the power k times minus 1 over 7 to the k power over k. But by a little algebra, minus 1 over 7 to the k power, by distributing that exponent, is minus 1 to the k power over 7 to the k power. Those cancel, and it's just negative 1 to the k power over k. Now, this is an alternating series that converges. So we'll have to include this number in our interval of convergence. 20 over 7 is part of the answer. It's one of the values that makes that series converge. Okay, let's check the other endpoint, 22 over 7. Now again, if I take this series right here, and I see where that x is, and I let it be 22 over 7, here's what it reduces to. By the same kind of algebra in this one, these cancel, and it leaves me 1 over k. Now this is a p-series that diverges. A p-series is a series that's 1 over n to a power p, or if you've got k, if that's your index, 1 over k to the power p, and those diverge if that power is 1 or less, which it is in this case. So 22 over 7 is not part of our answer. It's not a number that makes that series converge. Okay, so let's give our final answer like this. The interval of convergence is this preliminary answer I gave you, but we'll have to include 20 over 7 as part of it. So notice how I put a less than or equal to right there to include 20 over 7, but I'm still leaving out 22 over 7. This question on our assignment, it will call to write it in interval notation, even though this inequality means the same thing. So in interval notation, that bracket will say I'm including 20 over 7, and every number up to 22 over 7, but the parenthesis says I'm not including 22 over 7. So there's your interval of convergence. Any x in this interval will make this series converge to something, okay? What it would converge to, that will be beyond this question. Okay, what about the radius of convergence? Here's what we do to find that. We take the right endpoint of the interval minus the left endpoint of the interval, divide by 2. What that gives you is the width of the interval divided by 2. So that turns out to be 1 over 7 in this case. Maybe you can see why they might call this radius of convergence. So in a circle has a radius. And in a circle, we could say, well, the radius is the diameter divided by 2. So the diameter is kind of like the width of the circle divided by 2. So that's how you can think of this being called the radius of convergence. But nonetheless, that's how you find it. Okay, so there's our answer to the first question. Okay, now I want to talk a little bit about, well, what do power series do for us? So what, you have this series. So what, it converges if x is in that interval. What does that mean? Now, here in this question, we can scratch the surface to what that means. So here's another question that you'll find on the assignment. It says that this function can be approximated by this power series. They also refer to this as a Taylor polynomial, but that's it's from a power series. Okay, it is a power series in itself. So okay, I mean, I guess that could be another dimension to this. The fact that this is a series and it will behave like this function enough that they approximate each other. Okay, let's try that out though. Okay, so I have this function e to the minus x, and it can be approximated by this power series. Okay, and the question is, well, can you use this series to try and approximate what e to the power negative 0.05 is? Now, I will calculate both of those. If I want to use this function to tell you what e to the power negative 0.05 is, I'll let x be 0.05 and put it in there. And this is what I'll get with a calculator. If I want to then use this series to approximate that function, then I'll let x be 0.05 in it. Okay, so there it is. I took that series, I put 0.05 in for the x, and I calculated, and that's what I got. And these are very close to each other, as you would think. If this series generally behaves like that function in the sense that one could approximate the other, then I might expect to get values that are close. Now, this question also asks us about what's the absolute error. Well, so these are close, but by saying they're close, they are different at the same time. Okay, so the absolute error is an absolute value of how different they are. So if you took one minus the other and then took the absolute value, that would be the absolute error, which I get here. Or if you want scientific notation like it says in the question, I could get that. Okay, all right. Now, so we can use then power series to approximate functions. Now, in this case, where this comes from is that this is the general principle between this function and that series. That function e to the minus x is equivalent to this infinite power series, where that is a Taylor series for the function e to the minus x with a center at 0. And it happens to have an interval convergence of all numbers. Okay. Now, as far as how you can use this function with that center number to generate this series, it's all because of this formula right here. I've addressed that in other videos. Okay, so here's another video posted within the same lesson about how you would use that formula to get a Taylor series, given that you start with a function and a center. Okay, so you can watch that if you want to see more examples. Okay, but that's where this comes from. If it seems like it just comes out of nowhere. All right, so now that's the video. I'll make one more comment. Why would we want a series that approximates a function? Why not just use the function? Two answers to that. Well, it turns out that power series like this in place of functions are a technique that scientists and engineers use to solve these things called differential equations. Okay, differential equations are a favorite modeling technique for scientists and engineers. So they have that purpose, that we use them to solve certain kinds of problems that we encounter in science and math. The other reason I can give you is that, exponential functions, logarithms, trig functions are all transcendental functions. That means that they're beyond arithmetic. They're beyond addition, subtraction, multiplication, and division. They go beyond that, okay? But we have a little problem, like a calculator, the circuitry inside a calculator, it can only do arithmetic. It does addition, subtraction, multiplication, division. It doesn't really do trig functions, exponentials, and logarithms. But since power series are just arithmetic, addition, subtraction, multiplication, division, and since they can approximate functions such as transcendental functions, then they give a calculator the way to do exponentials, sine, cosine, logarithms, and so on. So they have that purpose also. In any case, so those are the two examples from the assignment. Hope that helps you. And if not, or if you run into problems with other examples, let me know and I can make more videos.